Now it's my pleasure to introduce Professor Wenjing Lou. Professor Lou is the WC English Endowed Professor of Computer Science at Virginia Tech and a fellow of both IEEE and ACM. Her research focuses on cybersecurity, particularly in the wireless networks, blockchain systems, and IoT security. She's a highly cited researcher and has received several awards, including the Virginia Tech Alumni Award for Research Excellence and the Infocom Test of Time Award. Prof. Lou has held leadership roles in IEEE and ACM conferences and served as program director at the U.S. National Science Foundation from 2014 to 2017. In our talk, she will present her innovative blockchain-based solutions for privacy, IT tracking, and spectrum access in the wireless networks. Now let's welcome Prof. Lou.
All right, so good afternoon. Thank you for inviting me to this venue, and I think it's a great pleasure to be here to meet so many blockchain experts and also to share some of our blockchain-related research and to learn from everybody. I think Dr. Zhang already introduced me. So I'm a person that works in the intersection of wireless networks and cybersecurity. So you see, my research interest covers a lot of security problems in networks, particularly wireless networks. I work on privacy-enhancing technology, and most recently I was dragged to trustworthy AI because of all my students are interested in AI, right? So I have a shameless plug-in here. So if you are students looking to do a PhD, or you are a postdoc looking for a position, you're a PhD student, you're graduating and looking for a postdoc, and you're interested in the topic, and you're welcome to contact me. All right, so let me talk a little bit about my blockchain research, right? So I think blockchain has some very nice security properties, right? The most cited one is really the decentralization, right? The fact that the blockchain does not rely on the trusted central authority and not even assume the trust among the participants, I think is the most desirable feature for blockchain, right? And those decentralization is actually accomplished by distributed consensus protocol. And to some extent, this is considered like a secure by design system, right? So to build the trust among a group of distrustful participants. And I think another most important property for blockchain is it provides validated, verifiable, immutable data recording, right? So this is accomplished by using the crypto algorithms, right? So you don't have to just trust this person who did everything right, right? And also it helps for transparency because it provides open and public auditability, right? So not only the people that get involved, but also third party can also verify the record. So those, I think, are the most important security properties for blockchain. And why not blockchain, right? So what's the downside for blockchain? I think there's actually only one, right? It's too expensive, right? So it's expensive is because it's a decentralization, right? And there's a cost associated with running all this decentralized distributed consensus protocol. From the storage point of view, instead of keeping one copy of the whole database, you're keeping tens, hundreds, thousands of the replicas, right? And from the communication point of view, it's not a server-to-client communication. Now it's a peer-to-peer communication, right? And then the computation, not to, we know how the POW-based consensus costs, right? So you perhaps have already seen all this, right? With all the energy consumed for the, the proof of work, all the computation we invest in the blockchain crypto systems, and they can only accomplish a very small portion of the throughput compared to the centralized system. So if we are looking at application, you have two options: centralized, decentralized. It's always centralized is more efficient, more effective, cheaper, right? But decentralized give you all the, the property, right? It's considered like a democracy in the digital world, right? All right, so my blockchain research, we started from study the consensus protocol, right? Because I think I'm a networking person, right? So consensus protocol is a key for how the blockchain system works, right? So I think we have a survey on distributed consensus protocol. I think they just mentioned this is a highly cited survey. It's already have almost 1,000 citations. So if you are a student who wants to get started on blockchain consensus protocol, you're welcome to read this paper. And then we also did some work on modeling the impact of the network connectivity on consensus security. So we know the 50% assumption is not strictly 50%. There are many factors that impact that, right? With network connectivity, if you are well connected or you're using something like a selfish mining, you can actually use much less than 50% of the actual resources to accomplish like 50% of the reward, right? So we also worked on some fundamental problems for blockchain, like a blockchain oracle problem, but we take a very different approach, right? We are not looking at confidentiality or integrity of the source. We are looking at the truthfulness of the source, because that's an external input going into the blockchain system. You have to make sure I would say it's a truthfulness, right? So we take a decentralized truth discovery approach to address this problem. And most recently, we're looking at blockchain sharding for the scalability problem, right? So, but today, what I would like to focus is not the fundamental blockchain security problems. We're interested in looking at the blockchain-enabled applications, right? So you must have already seen all this, right? So many of the applications, DeFi applications, that is enabled by the blockchain mostly due to the cryptocurrency and the smart contract supported by the blockchain technology, right? And there's other applications, interesting applications that is due to, the trustworthy record-keeping capability of the blockchain, right? So today, I want to show you a couple of, the blockchain-enabled capability or applications in wireless domain, right? So I want to introduce several systems we developed that include Privacy Guard, which is a private data usage control system, and AAK and UC Blocker, which is a system that blocks the unwanted calls and to realize anonymous authentication in mobile networks, and also the TriSys, and that's basically is a blockchain-based decentralized spectrum access system. So first, let me introduce Privacy Guard. So Privacy Guard, the goal for Privacy Guard is to realize a system that can do user private data usage control. It's not access control, but it's usage control. That means what your data is used for, right? This is to basically prevent the second-hand use of the private data. So since I have a video for this Privacy Guard, so I will just play the video. Can you play this?
In the upcoming evolution of the Internet of Things and cloud computing, the abundance of data is enabling many transformative applications. However, with the pervasive and large-scale data collection, storage, sharing, and analysis, the technologies that have greatly improved our daily life is now threatening our fundamental civil rights to privacy. Due to the highly sensitive nature of private data, the problem of misuse is becoming ever more concerning to individuals. In the notorious Facebook Cambridge Analytica scandal, more than 87 million Facebook users' profiles were harvested without consent and used for illegal political purposes. This data misuse problem is rooted in the fact that individuals will have no control over how their private data will be used when shared with other parties. Meanwhile, existing access control mechanisms do not prevent second-hand data misuse. To address the misuse problem, we formulate a new privacy goal called data usage control. Individuals should have full control over how their private data can be used by whom and when. This reflects the contextual nature of privacy. According to recent privacy legislation, represented by European Union's GDPR, individuals should have control over how their data can be used, such as the right to restrict processing and the right to object. Here you may wonder, is the data misusage problem only solvable by legal mechanisms?
In this work, we present a technical solution called Privacy Guard to prevent data misuse altogether and empower individual data owners with full control over both the access and usage of their private data by any data consumer, such as who can use my data for which operation at what condition. The plaintext data should never be exposed to other parties. In the meantime, data consumers expect the operation to be executed correctly and receive the execution result. And the usage records should be non-repudiable and can be audited later. To further enable a secure and sustainable data economy, where data owners can benefit from consumers' usage, we define the concept of a data transaction. In the simplest form, the consumer starts a data transaction with payment and receives the result in the end. And the whole transaction is recorded in the contract. To realize the above objectives, Privacy Guard employs two key technologies: blockchain smart contract and trusted execution environment. We use smart contracts for encoding the data owner's usage policy, enforcing the data transaction procedure, and keeping a non-repudiable record of usage history. We use TEE for enforcing the confidential off-chain execution of the data operation designated in the contract. This off-chain execution crucially enables confidentiality protection on private data and avoids costly on-chain computation. The operation is included in a secure container, known as a TEE enclave, which will execute the operation confidentially. An important functionality of TEE called remote attestation allows stakeholders such as the data owners and consumers to verify the integrity and authenticity of the enclave program, despite the lack of trust in the host platform in the cloud.
Putting everything together, Privacy Guard is composed of two planes. The control plane consists of the smart contracts and data owners and consumers' blockchain identities. The data plane contains off-chain entities of the participants and an off-chain contract execution environment that instantiates a TEE enclave for the specified operation. The consumer starts a data transaction by invoking an owner's contract. Then the data owner's off-chain entity iData agent and the consumer server attest the TEE enclave, and each establishes a secure channel to the enclave. The enclave fetches the encrypted data, and then the iData agent provisions the decryption key to the enclave. Then the enclave decrypts the data and executes the operation confidentially. At any point in the process, there is no exposure of the owner's plaintext data. Our system also enables wholesale data transactions with the new data broker entity, who represents a large number of data owners while achieving the same goal of usage control. There is one last thing: how to securely deliver the result to the consumer while concluding the data transaction at the same time.
In response, we developed a two-party commitment protocol to reach an atomic completion of the data transaction and result delivery. Essentially, the owner gets the payment and at the same time, the consumer gets the result. And the usage is recorded in the blockchain. The three objectives are either achieved together or aborted safely. This is secure against the collusion of any two parties. For more details, please walk by our poster or check out our paper published at European Symposium on Research in Computer Security 2020. Thanks for your attention.
All right. All right, so that's a privacy guard. So privacy guard is basically an example of, combines a smart contract blockchain technology with a TEE to manage the private data, manage data privacy, right? So the smart contract, the purpose is to basically allow you to write the policy, how your private data can be used, while the TEE is to execute whatever the data use applications, right? So TEE is to replace the smart contract, on-chain execution of the smart contract. Because if you run the smart contract on-chain, it will be very expensive. But how can you ensure that the off-chain execution is as secure as on-chain execution? So that's why we need a TEE for, right? So that's the one example. And recently, we have also been working on anonymous authentication in mobile networks. So the problems we're trying to address is the privacy problems in mobile networks, right? The mobile tracking problem. We know in mobile networks, your phone is constantly connecting to the cellular tower, and then the cellular tower will record where you are when there's a timestamp. And so if they have all this information, then they can pinpoint where you are. They can connect to the time and know your trajectory, right? And they also know who are with you at certain point, right? So those are pose significant privacy issues. So when the mobile network operator's database gets leaked or gets they sell the data, and then you perhaps will see headline like this, right? So in order to address this, the mobile tracking and mobile profiling problems, so we propose AAKA. It's an anonymous authentication and key agreement protocol. The current 5G network has 5G AKA, but we try to make it anonymous. And so this is anonymous authentication is not new, right? You have seen a lot of anonymous authentication protocols. So but for this research, our purpose is to have privacy against the mobile network operators, right? And we also need to have all the security properties of the 5G AKA. And because it's a privacy, so we also need to protocol to have accountability, right? So when under certain conditions, like there's a legal search warrant, then we need to do the lawful de-anonymization. So like those properties, right? So you may ask, how this is related to blockchain, right? It's related blockchain because for this AAKA, we leverage the DID, decentralized identifier framework, and the verifiable credentials that are supported in the DID framework, right? So, digital DID is a decentralized identifier, right? So it's basically a verifiable. It has a certain, the security properties associated with digital ID, and then it can be verified, right? So that's called a verifiable credential. So with that, we basically designed the AAKA, leverage the anonymous credential crypto tools. So the AAKA at the high level has two protocols. One is a subscription credential assurance protocol. That's when the user, imagine you're a mobile user, when you subscribe to the service or when you renew your service every month, when you make the payment, then your home network will issue you a credential, right? So with this credential, you can present this credential, then the third party can basically verify the security claim in your credential is true, right? So, then the second protocol is a presentation and verification protocol. So in this protocol, whenever the mobile user need to register to the network, need to connect to the network, they can generate a one-time verifiable credential, which called anonymous presentation, right? So from their own credential, they can generate a presentation, which is one time, right? And then they can show this one-time verifiable presentation to the service network, which network you want to connect, register. Then the network can verify your presentation and verify you are a legitimate user. So that's a basic concept, right? So I will skip all the, the details. It involves a lot of crypto algorithms, mainly anonymous credentials, and also in combination with zero trust, zero knowledge proof, and also the some Patterson commitment protocols, etc. Right? And so what we can actually accomplish is to have the user connected to the network anonymously. So I think an analogy is that the user has an unlimited number of the burner phone, that they have all different IDs. So they constantly changing the IDs, right? And those different IDs cannot be connected. So by that, they can hide they can have their privacy against the MNO, right? So this paper is published in this year's NDSS. And so we did the comparison for using the anonymous credential as the credential to do the authentication. So our results shows that it only adds approximately 50% of the computation overhead. And another similar work is called UC blocker. Right? So for UC blocker, we are trying to defend against the spam and the scam calls. I'm not sure about in other countries, but in the US, the spam and the scam calls are so annoying to the point that I do not answer any phone call that it's not in my the contact list, right? So while we are developing the AAKA, it occurs to us that if your phone has verifiable credential, it could be actually used to defend against or filter out all the spam or scam calls, unwanted calls. So this will be a very conservative approach, kind of a whitelist approach. That means only people you allowed will be able to call you, right? So, so the idea is that we will realize an end-to-end system. So by developing the sort of mobile user apps to allow user to define the policy who can call them, right? And so again, this is a leverage the DID framework, right? And also use the attribute-based anonymous credentials. So the callees can set up the attribute-based caller authentication policy, right? So callees can set up the policy who can call me. And then we use the attribute-based authentication to to realize the caller authentication, and then we will, once the authentication is successful, then we will generate a very code and then use that very code. That means this author has been authorized, this caller has been authorized to call, and then this call will be successful. Of course, we did a lot of work to actually realize this kind of a system in the mobile networks. The caller authentication is done separately from the call session initiation, because the authentication is actually done in out-of-band mechanism, right? So, but then the call session initiation is through the regular telephone networks. The trick we did is basically have this one-time verification code embedded using replace the caller ID using this one-time verification code, right? So I think there are important question to answer, like who will issue this, the credentials, right? So in this case, colleague can issue these credentials because you can use something out-of-band mechanism like the Facebook or social media, so make friends, right? So when you add friends, when you accept the friend request, you can give the credential to the other party, then they can call you. And it can get, it can be issued by the trusted authority, or you can establish a mobile virtual network operators to start a new business just to provide, to issue these credentials, right? So yeah, I can only give you some basic concept for those new capabilities, right? So for the next application I want to mention is a dynamic spectrum sharing, right? So in the for the radio spectrum, actually, is the most important resources for wireless communication and sensing, right? But that's not the only services. It also been used by the many important scientific studies like radio astronomy and national security applications like military, radar, etc. So for the spectrum use, there's only two types of use in the past, right? Licensed and unlicensed, right? About a decade ago, then the US started to consider the third type of spectrum usage, which is a dynamic shared use. That's basically means when the incumbent is not using it, then the other service could use this very valuable spectrum resources. And so in the heart of this dynamic spectrum sharing is basically a spectrum management system, right? So over the years, the spectrum management system already shifted from the sensing-based to database-driven, right? So the very noticeable and successful example is a spectrum access SAS in the 3.5 gigahertz CBRS band in US. It's already been commercially deployed, right? So this SAS is basically a client-server model, right? It's centralized, and then the client will make request to the server, then the server will make the assignment, right? So, but moving forward, there will be multiple SAS administrators, just there are multiple mobile network operators, right? Each one of them will serve their own customers, right? So just like the current mobile network operators. But what's different is that the current mobile network operators have their exclusive use spectrum, but the SAS administrators will need to share the spectrum. They are going to make the assignment in a common shared spectrum. So this requires those SAS administrators to exchange information and do a unified assignment, right? Wireless mobile network operators are notoriously known as not sharing any data with each other, right? So this raises concerns, right? So where we start to look at the blockchain-based SAS system, actually suggested by our industry collaborators, right? As mentioned in, I think, the FCC chairwoman Jessica Rosenwals's comments, blockchain might be the right mechanism to address the trust issues among the SAS administrators, right? And also the blockchain's capability to keep track of the transactions and recording all the transactions provide FCC needed auditing capability, all right? So we tried the blockchain-based decentralized SAS. I think the first work is BDSAS. Basically, we implemented a two-layer SAS-based SAS system, just decentralized a centralized system, right? So this is this system demonstrates the feasibility of building the blockchain-based SAS that meeting the capacity and the latency requirement. But they can realize automatic, transparent, and correct execution. But the downside or the missing piece is that we realized a very simple, the allocation algorithm, and there's a lack of spectrum privacy protection, right? So I think recently we actually got funds from NSF, from the NSF Spectrum program, to further the study to generalize blockchain-based, the SAS system. So we further developed a tri-SAS, which leveraged the blockchain database, and but we modified instead of directly using the blockchain system, we also we modified the system so that we can support a proprietary allocation algorithm, so every administrators can run their own algorithm. And we're only going to synchronize, reach consensus on the results, all right? So this actually is a very recent work published in this year, Asia CCS. I know I'm running out of time, so yeah, so it's just the final remarks. So I think if you're thinking about using a blockchain, build a blockchain-based system, you must justify the use of blockchain, right? Because it's very expensive technology, right? I think the major justification is basically this trust among the participants and also the auditability of the results. If that's a must, right? And so many people ask me, some of the applications, you don't have to use a blockchain, right? You can maybe just use Byzantine fault-tolerant protocols. Yeah, I think that's true, right? In some cases, that's true if you are looking at a particular application. But what I really like about the blockchain is that it's a convergence technology, right? So it provides this platform that can nicely integrate other components and accomplish much bigger things. All right, so I think that's all for my talk. Thank you.
Any questions about Prof.
Yeah, thanks, Professor Lou. Just a very quick one. For your work of privacy guard, right? Can we deploy your smart contract on L2 or even on L3 to further reduce the cost? Can we deploy the smart contract? Not on the public blockchain directly, right? But on L2 or L3, roll-ups, something like this.
I think for the privacy guard, our concern is, the example we used is running machine learning algorithms, right? So when you run machine learning, you need to have the data from all different participants. So the machine learning is a quite intensive, program to run. So it's not really economical to run on-chain. It's impossible, right? So we want to shift it off-chain. So this is just one thing that you can move the computation-intensive tasks off-chain, but to keep the minimal, the logics on-chain, right? So, but other, I think the techniques like a layer 2, layer 3, I suppose if they are general to
smart contract,
right,
that should be okay.
I think it's perhaps you can combine all these technologies, but we did not really look at it.
Okay, yeah, thanks a lot.
Right, thank you.
Any further questions?
Thank you for the interesting talk. So I guess my question is more like a clarification question on this, on your work using anonymous credential for spam or scan code detection. So in that case, how is it different? So what's the unique capability? Does it bring compared to the baseline solution where right, so you just use, you mentioned it before, you just use your phone to block any incoming calls that is not in the local contact list?
I think the baseline, you can do the blacklist, right? So that means you have you block certain numbers, right? That's a blacklist. But the spam calls, the root cause for spam calls is a voice over IP. So for all voice over IP, you know, the spammers can register many, many legitimate phone numbers, and they can also fabricate the caller IDs. So the official solution for this is stir and shaken, right? So FCC is promoting that, but that is a network-based solution. So that the network, the service, the mobile service providers are checking, you know, the trust level of those phone numbers, right? But this need all the carriers to buy in and to support this. But for the, you know, the IP from remote side, you know, not within your jurisdiction, you cannot prevent that. Yeah, the current, I think, the baseline you said is a sort of the blacklist, right? So if this already call, you recognize that, you block that. But ours is more restrictive, it's a whitelist.
Oh, okay, thank you.
Right, so that means you have to establish the permission. It's like an old culture when you want to call somebody, you ask the number, and if they give you a number, you can call, otherwise don't call. Any other questions? All right. Thank you.